In this video, we're going to be taking a look at reference angles. And for this video, because I'm trying to keep this as part of our review of the trig basics, I'm going to only give us examples where we have a nice reference angle. In degrees, that means 30, 45, or 60 degrees. In radians, of course, that's pi over 6, pi over 4, or pi over 3. Okay. Now, for angles that have a nice reference angle like that, if you've memorized the unit circle, you don't need to work through reference angles in order to evaluate the trig functions. However, not all angles have a nice reference angle. If you have an angle and its reference angle is arctan of 7, you're going to need to know how to use reference angles. So if you feel comfortable with that topic, that's fine. You don't need to necessarily watch this video. But if you've memorized the unit circle, but you don't really feel comfortable using reference angles, if you have a messy example where the reference angle isn't one of those 3 nice ones, then you definitely do want to pay attention. So let me just tell you what the setup is that I have on the board here. This lovely picture is 3 circles, all centered at the origin. The blue one is the unit circle. Okay. The green one is the circle of radius 2. And I've set that up because if our reference angle is 30 degrees or 60 degrees, I want to be using my 30, 60, 90 triangle. This is the version of the 30, 60, 90 triangle that I usually use. I start with an equilateral triangle of side length 2, and then my sides are 1, 2, and root 3. Now, if I'm working with a 30-degree angle, that's going to make the hypotenuse, which is 2, line up with a radius of that circle. So I can work with this triangle. The hypotenuse here is the radius, of that green circle. However, I know it's often nice to work with the unit circle. So I have a scale model of the 30, 60, 90 triangle where the hypotenuse is 1. So if I have a 30-degree angle in standard position, I can work with this triangle. Now, that hypotenuse of 1 is a radius of the unit circle. And of course, these triangles are exactly the same size and shape. So if I've got a 30-degree angle, it's going to intersect the unit circle here. It's going to intersect the circle of radius 2 here. I'm just choosing, am I working with this triangle or this triangle, if I'm using triangles to evaluate things. The medium-sized circle here in red is of radius root 2. We're going to be using that when we have 45 degrees as our reference angle, because the version of the 45, 45, 90 that I usually draw has legs of length 1, but that makes the hypotenuse root 2. So I made it so that that hypotenuse is the radius of the red circle, and then here's a scale model of that where the hypotenuse is just 1 to coincide with the radius of the unit circle. Okay, so I've drawn a 150-degree angle on the board here, and I would like to evaluate cosine of 150 degrees. And so I'm going to do that as a 2-step process. Now, it's not necessary that you do things exactly the same way I do. It's important that you understand what's going on. Okay, so my 2-step process, I'm going to figure out the sign, whether it's positive or negative, and then I'm going to figure out the absolute value that I attach to that sign. Now I know, by definition, the point here on the unit circle where this terminal ray intersects is cosine of 150 degrees, comma, sine of 150 degrees. So we're looking at the x value right here. Well, since we're in quadrant 2, I can see by inspection that that's going to be negative. So I can determine the sign, S-I-G-N, plus or minus, by simply looking at the quadrant that my terminal ray is in. Okay. All right, so now I want to figure out the absolute value. How negative is it? Okay. Well, for that, I'm going to work with my reference angle. Now, the reference angle is always the angle I get by dropping a perpendicular to the x-axis. So the reference angle is the angle always counted as a positive acute angle between the terminal ray of my angle and the x-axis. So since this would give me 180 degrees and that's 150, that's going to be 30 degrees. So my reference angle in this particular case is 30 degrees. Now, if I take a look, I basically want to know how big this side length is right here. I'm going to the left. I've already accounted for that with the negative sign. I want to know how far I'm going to the left. So I want to know the actual length of that side of that triangle. Well, notice this is my 30 degrees right here. If I drew it in standard position, that would put me at this point right here, which would be cosine of 30 degrees, sine of 30 degrees. Now I can see just from the symmetry that the y values of these 2 points are exactly the same. That's this distance, and we're going up in both cases. The x values, on the other hand, are just exact opposites, because when I'm in quadrant 1, so that we're going to the right, my x value is positive. In quadrant 2, going to the left, my x value is negative. So I can say that cosine of the reference angle gives me the absolute value. It tells me how long the side is, and I attach that to the plus or minus sign that's determined by the quadrant. So it's going to be negative, let's see, cosine of 30 degrees, but cosine of 30 degrees I can get. And usually what I do is I go to this triangle. I say, now that I know that that's what I need to calculate, let me go to my familiar friend. Cosine would be root 3 over 2, so negative root 3 over 2. Now, of course, if I'm using the unit circle here, I'm looking at that side length. That side length was this side right here. That is root 3 over 2. All I'm doing is saying, hey, if I want to, I could use this triangle instead. But if I use the bigger triangle to calculate cosine, I need to remember that it's not just going to be the x value, it's going to be adjacent over hypotenuse, so root 3 over 2. But very often I'm talking about the unit circle. Once I establish what my reference angle is, I usually go to the triangle I'm most comfortable with, which is usually the bigger one. So it's not the one that would fit onto the unit circle, but it still gives me the right ratio of the side lengths. Because remember, with right triangle trigonometry, the whole idea behind that is that any two right triangles with the same acute angle are going to be similar. So the ratio of opposite and hypotenuse is going to be the same regardless of the size of the triangle. Okay, so I basically do a two-step process. Get the sign based on what quadrant we're in, and then the absolute value. Okay, so step 1 is to find the SIGN, and that's by looking at the quadrant. And then step 2 is to get the absolute value, which is just the trig function evaluated at the reference angle. Now I mentioned that the reference angle we always get by dropping a perpendicular with the x-axis. Let me just show you why. I'm going to actually show you with the bigger circle, just because it's bigger, it's easier to see. Okay, so here was my 30-degree angle. The longer side is on the x-axis. If I make a 30-degree angle with the x-axis, that longer side is still my horizontal distance. Notice, if I were to make my 30-degree angle with the y-axis here, now the longer side is on the y-axis. Okay. So I'm not preserving horizontal and vertical distances if I make the reference angle with the y-axis. So I never do. I always make it with the x-axis. Same thing here. Okay. Here's what I get if I make a 30-degree angle with the x-axis. Notice the longer side is the horizontal side. And over here, a 30-degree angle with the x-axis, the longer side is the horizontal side. If I were to switch and make that 30-degree angle with the y-axis, now I've switched the roles of horizontal and vertical, and I don't want to do that. So the reference angle is always, always, always with the x-axis. Okay, now, some of you may be in the habit of just drawing in a triangle and labeling the signed side lengths. So some of you might have, I'm just going to erase this. some of you might have done something like this. Said, okay, if here's 150 degrees, that makes this 30 degrees, and then you would label, and depending on which size you want to use, I usually use 2. So you'd say that's that's 1, and that's negative root 3 right there. That's labeling the signed sides of things. If you label things with signed sides, then you can sort of do the sign and the absolute value in one step just using SOHCAHTOA. I actually prefer to do things as 2 separate steps, dealing with the SIGN as a separate step from the absolute value. The reason is just that they're going to hit some problems later on where we're not just working with numbers, but we're working with variables. And if we draw the signed sides, it's easy to get dependent on seeing that negative sign to know that that's a negative number. Works great for numbers. That's positive. I know that because there's no negative sign in front of it. And that's negative. And I know that because there's a negative sign in front of it. This always makes me feel very smart when I explain how I know whether numbers are positive or negative. But that trick doesn't work with variables. X can represent either a positive or a negative number. So I've sort of trained myself, think about the plus or minus signs, and I do that by always forcing myself to do it as a separate step. Okay, so let's do one more together, and then I'll give you folks a few to try. Okay, so let's try looking at tangent of 3 pi over 4. So this time I'm working in radians, so I'm going to need to figure out where this is on the unit circle. So let me erase what I have. You know what, I'm just going to draw a new picture. Okay. So, this would be 0. I know this is pi over 2. This would correspond to pi. Now, 3 pi over 4 is smaller than pi. I can sort of see that. But sometimes it's a little bit hard to tell where things are. What can be very helpful is to just get a common denominator. Pi over 2, if I were to multiply that by 2 halves, that's 2 pi over 4. I can see that 3 pi over 4 is going to be bigger than that. Pi, I could multiply that by 1 in the form of 4/4. That's the same as 4 pi over 4. Well, now it's very clear that 3 pi over 4 is between 2 pi over 4 and 4 pi over 4. So getting a common denominator can make it very much easier to see where an angle is. Okay, so there's my 3 pi over 4. Okay. So I'm going to just work this out as tangent of 3 pi over 4, 2-step process. I'm going to figure out the sign, and then I'm going to attach the absolute value. And I know the absolute value will just be tangent of my reference angle. Okay, so circle definition of tangent is that it's y over x. We're in quadrant 2 again, so y is positive, but x is negative. So we're getting a positive divided by a negative. That's going to be negative. And then what's my reference angle? Well, if this was 3 pi over 4 and that was 4 pi over 4, looks like my reference angle is pi over 4. And I want to recognize that that's my 45-degree angle. So I've erased it, so I'll draw it again. Here's my 45, 45, 90 triangle. Now, maybe this was the unit circle, but that's okay. I used that to figure out what quadrant I was in and what my reference angle was. Now I'm just going to use the 45, 45, 90 triangle that I like best, which has as the two legs 1 and 1, and tangent would just be 1 over 1 or 1. So that tangent of 3 pi over 4 is equal to negative 1. All right, so I'm just going to give you folks 2 problems to try. This video's been going for a little while, so what I'll do is give you these problems, end this video, and then in the next video we'll go over them. So let's try sine of negative 5 pi over 6, and then let's try secant of negative pi over 4. So try both of those, and then in the next video, as I said, we'll go over them together.